All right, now let's move over to these. Now we're going to prove that the halting problem is undecidable. All right? And just try to follow along and understand my words, because my belief, is wrong, of course, but my fantasy is that this isn't so hard. And if you don't panic and you just follow each step, you'll believe it, right? Now, the problem is there are lots of steps. And will you be able to hold all your steps, all those steps in your brain at the same time and really, really deeply, deeply understand it? Maybe not, right? But hopefully you can follow the steps. And hopefully, if you're in a Google interview and they say, prove to me that the halting problem is undecidable, right? Which wouldn't be a bad test question, right? If you wanted to weed out the people who have good abstract thinking, you take a topic that everybody who has a computer science degree in the world has learned, and you ask them to do it. Right? I think I would do that if I had an interview question, right? In fact, I have a grad student who wants to come already. Maybe I should ask him, right? See what he could do. All right, everybody ready for this? All right. So you Google it. There's lots of resources out there, right? So somebody gave me this link that describes it. All right? And so this proof, we're going to first prove it on one page, I think. I thought I cut out the one-page proof. But you're not going to understand it at all, right? So then we'll try to go down and get what's happening a little bit better, right? Suppose there was a working algorithm, right? This says, everybody know what the halting problem is? The input is the description of a Turing machine and an input to it. And the output is, yes, this Turing machine will eventually stop, or no, it won't. Right? And you might think, well, obviously that's computable. Why? You give me a Turing machine and an input, what do? I run it. Right? And if it stops, I say it stops. Right? But if it doesn't stop, right? All right, so let's see. Here's an algorithm, right? What does this algorithm do? It's a Turing machine. Halt is a Turing machine. You give it a description of a Turing machine and an input, and it tells you whether it halts or not, right? So from it, a lot of the things we do is reductions. If you can solve one problem using a Turing machine, then I'm going to build from that Turing machine another Turing machine that can, right? One program calls another program as a subroutine, right? So we're going to design another algorithm that uses that as a subroutine. What does it do? We're going to call it p-hard. And what does it do? It takes m as input. And if m halts on m, right? And now how do we know that? Well, we have the program halt. So we can ask, does m halt on m? Right? And if m halts on m, what do we do? What does p-hard do? It runs forever. Right? So one thing about this program halt is we know it always halts. Right? Halt always halts. And tells us whether or not m halts. Right? So here we're giving m. We ask halt whether m halts on input halt. Right? Here we take what. Does everybody catch this? Here's what do we have to give halt? We have to give it a description of a Turing machine and a description of an input. And we're using m, which is a finite string, in two ways. Both as it's the Turing machine we care about, and we use the description of the Turing machine as the string which we run the Turing machine on. Right? Are people following that? Right? So, and then if m doesn't halt on m, what do? We halt. Right? Everybody buy what we're doing here? It's basically, it's kind of you stick a knife in and you twist it, right? We need the set of all. Set of all. Let's talk about books. That some books list books, right? So you have the set of all books that list books. Now, some books that list books list themselves, right? So you have the set of all books that list books but don't contain themselves, right? Have you heard those sort of things? They're paradoxes. So anyway, let's get our paradox. Here's the question. If halt has a Turing machine, then P hard has a Turing machine, right? You just run this code. Now, P hard has a Turing machine. So P hard's Turing machine has a description. And we're going to give that description to the Turing machine, and we're going to ask, does it halt or not? Right? And what's the thing? Well, if the Turing machine P hard, here's the Turing machine, here's the description of the string. If P hard halts on P hard, then what? Well, what's P hard supposed to do on M? P hard on M halts only if M doesn't run on M. But now we're giving it P hard. So P hard halts even only if P hard doesn't halt. Right? So if P hard halts, then it doesn't halt. And that's a contradiction. Everybody buy that? That's it. That's the entire proof. And if you're expecting something deeper, it's not going to happen. That's the proof. Right? That Turing got famous for. Everybody got it? Now, let's try it again. All right? So first, right, I don't know, we give a little history. You might have seen these slides already. But, Euclid came up with the first algorithm, say for GCD, and he was happy, right? And then, why are we happy? Because all math has to do with God. And so we now have right? All they cared about is there were problems that we had algorithms for and problems we don't have algorithms for, right? And then Hilbert in 1900 had a conference in Paris listing big open problems. It was a fantastic lecture. Why? Because every problem he listed either still isn't solved or opened up a huge field of mathematics, right? It really was a fantastic list of open problems, all right? And one of his problems was, are some computational problems uncomputable, right? And if you want to say a problem's computable, you just have to give me an algorithm and convince me that it solves it, right? But if you want to prove to me that things are uncomputable, then you really have to well know what is an algorithm, right? Because you have to prove every possible algorithm doesn't solve this problem, right? So that's what Turing did. He defined what an algorithm was, and he proved that the halting problem doesn't have an algorithm, right? All right, so let's just be clear about what these problems are, right? The halting problem takes the description of a Turing machine and an input and tells you whether that Turing machine runs on that input. And you'll note here I've sort of differentiated between this is a Turing machine and this is its description, right? Slightly different objects, right? Everybody got that? Right? This is what I said. Obvious algorithm. Run it, right? But if it doesn't halt, what's the answer? Right? When do you stop? Right? Remember, if you're going to solve this problem, on every input, you have to halt to know the answer. Right? And if your input is a Turing machine that doesn't halt, how are you ever going to know? Right? Everybody following this? All right, so let's give some examples. Right? So if you think it's undecidable, then how do professors ever mark? Well, it's because practically we know things, right? Practically, if I asked you, does this algorithm halt, what do you say? You say it halts, right? If I give you this algorithm, what do you say? It doesn't halt, right? Now, suppose I give you this algorithm. Now, I want to know if it halts or not. Well, I don't know if you've heard of this problem, right? It was famous, and then it was, and then somebody solved it 10 years ago, 20 years ago, I don't know, within my adult life, right? What's the problem? Is the claim was for every 4 integers, a, b, c, and z, bigger than 2, a to the z plus b to the z equals c to the z. People conjectured that was true, right? And what does this algorithm do? Well, if the conjecture is true, the conjecture is that they're not equal, right? They can be equal for z equals 2, right? 4 squared plus 5, 3 squared plus 4 squared equals 5 squared, right? It's a little triangle, right? But for z's bigger than 2, it's believed not to be true. So what does this algorithm do? It halts if the conjecture is false, right? And it runs forever if the conjecture is not. Oh, that's what it's called, Fermat's last theorem, right? So if I give you this and ask you whether it halts or not, well, they finally figured it out, but it took them 100 years of math to figure it out, right? So here's definitely a hard problem. Everybody follow that? And what's the definition of chaos, right? My definition of chaos is that it's all computable, right? Given this state, I know where I'll be next state, and I'll know where I'll be next state. I know where I'll be next state. But if you ask me where I will be in 1 billion years, the only way of knowing is to run it and find out, right? Right? I can, if we knew everything about the weather today, we could predict the weather in 1/1000th of a second. But predicting it 100 million years from now is just, right? So here's some loop that does some chaotic thing. How do I know whether it'll halt? Really, only by running it, right? Does that make sense? And if you think chaos is just, think about a pool table, right? Put a bunch of balls on the table, and you shoot, and you'll know, oh, I hit this ball, and then I'll bounce. In fact, have all these ones circles they don't move, right? Some have circles, and now I have a ball, and I want to know what it does, right? Well, a little error here multiplies, and then that error multiplies, and that error multiplies. You have to know which direction I'm going to infinite precision to know what it's going to do for infinite time, right? Really simple example. All right, so how can we know without running it forever? Everybody getting this? So, yeah? Oh, the answer is the definition of chaos is you don't... This one? Oh, the conjecture is true. Conjecture is true. In fact, if you want me to give you a little route for India, they all study to get into the IITs. And I went to the IITs for a year, and those guys were so smart. So we're sitting on the train, and they just knew everything. I would ask them questions. Anything I asked these students, they would know, right? So this came up. And on the train, these undergrad students were telling me how to prove the conjecture for most values, right? It was only a few values that were open, and for most values they had a proof. And these students knew it. I don't know it. They told me on the train. Don't ask me what it was. All right? All right, so here's another little program. Simple little program, right? You take 2 numbers, x and y, right? 2 real numbers. And you think about z as being a complex number, right? It's a number in the complex plane. And what do? You start with this value, z, and you update this complex number. How do you update it? Something nonlinear, right? I don't even know if this is a good nonlinear, but right, something nonlinear. And then you add some c to it, and you loop. And when do you and you exit if something interesting happens, right? It converges to one point, or does it go off into space, or does it, right? You ask this. And there's this c parameter, right? And c is also a complex number, right? So now you want to plot, right? In fact, if I'm not mistaken, xy is going to be some fixed number, and here I'm plotting the value of c, right? C is a constant, so c has a real and imaginary part, and a point on here tells me the value of c, and then the color tells me what this program does, right? You've all seen this, right? It's a Mandelbrot set. Chaos, right? Here you know what it's going to do. Here you know what it's going to do. You get some nuance in here, who knows what it's going to do, right? Everybody know this? All right, so why is this useful? Well, your boss tells you some problem, and you say, hey, if I could solve that problem, I could solve the halting problem, which is impossible, right? So it tells us that there's no algorithm for some problems. Some really good problems that you might want to know the answers to, right? You're in the world, you say, hey, I want to solve this problem, right? Some very small number of problems have polytime solutions. Some are NP-complete, meaning we don't think they have polytime solutions. Some are undecidable. All right? So, all right. You ready for we're going to go through the proof a little slower, right? First off, right, you know what a computational problem is. You all know what a Turing machine is, right? This is a slide you've seen before. And what are we trying to prove, right? You know, it's all about first-order logic. What are we trying to prove? We're trying to prove if it's computable, then there exists the Turing machine such that on all inputs, the Turing machine gives the right answer, right? And what do we want to prove, right? Everybody here, how do you do it? How do you prove P is computable? Hey, I have an algorithm. Great, I have an input. Let's see if it works. Everybody know this game? Right? So, now it's uncomputable. Right? We're saying for every Turing machine, there exists an input on which it gives the wrong answer. Right? Everybody got that? So, he says, hey, I have a Turing machine that solves P. And he says, hey, no you don't, because I have an input on which it gives the wrong answer. Everybody remember the game? So we're going to play this game. Right? So, here's what we want to prove. Right? At the moment, all we want to prove is that there exists, we wanted an uncomputable problem. Right? And more than we want it to be a constructive proof. Right? That counting argument, it proves that there exists uncomputable problems. Right? But I want to know it. Tell me one. Tell me some uncomputable problem. Right? So we're saying there exists a problem that I can describe to you. It's a problem that actually has a finite description. I can tell it to you. That's that for every Turing machine, there's an input on which that Turing machine will give me the wrong answer. Right? Everybody understand the game? All we're going to be doing here is a really nice, easy playing of this game. All right? Are people following? All right. So how do we play the game? Right? Our goal is to prove that there exists such a problem. Right? So what do we want that problem to do? We want it to fail for every input, for every Turing machine. Right? I need to give you a problem such that for every Turing machine it fails. And why does it fail? It fails because there's some input on which it fails. Right? And I'm going to call that input I sub m. Why? Because it's the input that witnesses the fact that the Turing machine fails. Right? So here, what's true? M of I sub m doesn't equal P hard of I sub m. Right? Everybody understand that? So given a Turing machine, input I sub m witnesses the fact that the problem is uncomputable. Right? And this is just, right, this first order logic problem. Everybody understand what we're doing here? All right, so let's play the game. So we start by this guy has to describe a hard problem, right? And he has to actually tell us what the problem is. But I don't know how to do it yet, so we're going to pause. But imagine he has to give this information, right? And then, right, we're just playing the game. I give you this. And what does the adversary do? The adversary gives a Turing machine, M, that is supposed to solve my hard problem, right? And then what I do, I give an I sub M that is supposed to defeat my adversary's Turing machine, right? We're going to later, I think maybe it's right now, we use the word nemesis. This is every Turing machine needs a nemesis input, right? You guys know the word nemesis if you've read comic books, right? What's the nemesis of Superman? Kryptonite, right? All right, so everybody got this game? Now we're supposed to play this game in this, here is the nemesis, right? We say I sub M is M's nemesis because it proves that M doesn't solve P hard, right? Everybody follow this? All right, so this is the way you're supposed to play the game. You're supposed to play it in this order, right? But look at the Boolagoo guy. He has a number of tasks. He has to define this P-hard problem, and he has to do the task for every M, he has to supply an IM, right? And he's supposed to do it in this order, but he's going to plan ahead. Before he defines this P-hard, he's going to do this first. And why? It seems weird, but that's what he's going to do, right? Usually, you choose the input after knowing the P-hard problem, right? But we're going to do them in other orders, right? What we're going to first do is choose our nemesis, right? So for every Turing machine M, I'm going to choose some input that's going to defeat that M. Right? Everybody buy this? A defeating nemesis, right? And now, what do we need? What property do we need of this input? Actually, no properties. Every M needs a nemesis. That's all we have. And there's a little caveat, though. Two Turing machines can't share the same nemesis, right? Every Turing machine needs an input that will defeat it to show that it can't solve my P-hard problem. And every two Turing machines need their own nemesis. All right, does that make sense? So, what should we use as a nemesis? I give you a Turing machine. You tell me an input which is unique only to it. Itself, right? Each Turing machine has a finite description. So each Turing machine, right? One key property of Turing machines is they have a finite description. So what is our nemesis going to be? Our nemesis will be the description of the Turing machine itself. Right? Does that make sense? Now, why do we do this? No reason. Only because we need every Turing machine to have a nemesis input, and it needs to be unique. And this is a nice, easy way to do it. Right? Now, people might say, what does this mean? How can you take a Turing machine and give it this description of itself? That seems weird, right? But let's just be clarified, it's not that weird. Somebody wrote the Java compiler, right? And what language did he write it in? She wrote it in. She might have written the compiler in Java, right? So how did they compile? Who wrote the very first compiler? Right? How did they compile the very first compiler? Right? You need compilers to compile compilers. You need editors. The code for the editor needs to be edited. What program do you use to edit the editor? You could use itself. It's not completely, it's kind of bootstrapping, but it's not completely unheard of. Right? Now, you know, I've been to plenty of hippie gatherings, and they talk about woo-woo things, and they often talk about somehow you feed your inputs. You know, they've read enough of these paradoxes to think they're exciting, and they get some deep meaning out of the fact that we're taking ourselves as our own input, right? It doesn't actually mean that much. But, right, so this just says don't read too much into it, right? All we're doing is assigning a nemesis to every Turing machine. Everybody got it? So what do we know? We know every Turing machine's nemesis. And so now, once we decided that, now let's decide what our p-hard problem is going to be. All right? Let's see, what do we need for it? Right? Well, if this nemesis is going to tell me that Turing machine M doesn't solve this problem, what do I need? I need that, what does this Turing machine do on its nemesis input? Right? This is the nemesis input. Given a Turing machine, we have to prove this Turing machine doesn't solve problem P. How do we show that M doesn't solve P? We find some nemesis input in which it gives the wrong answer. Right? So what do we need? We need this statement here. Right? We need that M on its nemesis gives the wrong answer. Right? All right, so now, no problem. That says we don't have a problem, but this is a problem. So anyway, how do we define p-hard? Right? Well, how do you define a problem? For every possible input, I have to tell you what the output is. Right? All right, so what I'm going to do, I'm going to say, given an input, I have to define what p-hard does. If my input happens to be the description of a Turing machine, then the required output is anything different than what that Turing machine does on itself. Right? Here we're defining p-hard. You give me some weird string, garbage string, then I don't care what the output is. Right? But if you give me a description of a Turing machine, then my required output is the following. Find out what M does on M and do something different. Right? Does everybody follow that? So, let's do it. And we're going to call the problem the not diagonal problem. And maybe here I'm going to describe the diagonal of what? Right? What's these? Remember each Turing machine has a finite description, and each Turing machine is countable, and hence I can list the Turing machines, right? And what's true about this list? Will I ever get to them all? No. But given any Turing machine, it's on this list, right? Similarly, let's list all possible inputs here, right? For each given finite input, it's somewhere in this list, right? Now, what are we going to fill this matrix up? We're going to say, what does this for every spot in this matrix, we're going to ask, what does this Turing machine do on this input? On this Turing machine, on this input, what it does is it stops and says hi, right? Nice thing for a Turing machine to do, right? What does this Turing machine do on this input? It runs forever. Right? We can fill in this whole matrix. Right? Now, let's order the inputs and order the Turing machines in the same way. So that when you got the diagonal, what's the diagonal? It's running a Turing machine on its own description. Right? Does that make sense? That's the diagonal. Right? So this is diagonal. What does this Turing machine do on its own description? Right? So there's this Turing machine on its own description says, I love myself, which is a good New Age thing to say when you take yourself as input. Right? What does this Turing machine do on its own input? It runs forever. Right? So what is the not diagonal problem going to do? It's going to take the diagonal and change it. Right? So what it's going to do, instead of forward, right? Instead of saying I love myself, we'll change it to saying I hate myself. And instead of halting, instead of running forever, we're going to halt and laugh. Right? Everybody say we just changed it. So that's how we define the not diagonal problem. Given an input, we can think about it both as the description of a Turing machine and the description of an input. We can ask what that Turing machine does on itself, and we can change the answer. Everybody got that? It's a perfectly good computational problem that I just described to you. Right? Everybody buy that? So now, enough chat, let's play the game. All right? Now we can just prove this statement, right? All right, so how do we prove the game? There's an exists here, right? So I have to tell you what p-hard is. And what's p-hard? Well, for input, on every input I tell you what it does. If the input describes the Turing machine, then the required output is anything different than M does on M. We describe p-hard, right? Now, you're going to love this. It's so short now, right? It's so short. Now, what does my adversary do? He gives me a Turing machine that's claiming to solve the problem, right? I have a Turing machine. And then what does the prover do? He has to come up with a nemesis input. What's that input? It's the description of the Turing machine just given, right? And then we have to see, does this Turing machine that the red guy give me solve the problem on the input that the blue guy came up with? No. No. Why does it not? Well, because M doesn't give the right answer to p-hard on this input. It doesn't. All right, everybody follow this? Okay, we can breathe now. And that proves us that the not diagonal problem is uncomputable. Right? Everybody got that? Now we want to prove that the halting problem is undecidable. All right? So, what effectively does the problem not diagonal require? It requires that for every Turing machine description, it has to halt and do something different than M on M, right? And we want to show that that's undecidable, right? So, no, we already know that's undecidable. Now, let's again think about what it describes. It says for every input M, it needs to, in order to do something different, well, more or less it needs to know what M does on M, right? You give it an input M, it needs to know what M does on M. And we know that that's undecidable, right? So here's another problem, right? And I'm listing these because these are subtleties that I know students get confused by, right? Here's another problem. Remember we talked about the universal Turing machine, right? What does the universal Turing machine do? It takes as input the description of a machine, and it finds out what it does on various input. It simulates it. So this problem here, what it does is it finds out what M does on M, right? But the problem is that if M on M doesn't halt, then what the simulator does is it doesn't halt. Right? Does that make sense? Here are two problems. They look identical. On both, they take as input the description of a Turing machine. And in both, they want to know what does M do on M. And on both, if the Turing machine halts, then it knows what it does. But in the first problem, if N runs forever, then the first problem has to halt to know it. And the second problem can run forever. Right? Does that make sense? So, right, this one's undecidable and this one's doable. Right? They seem to be the same. How are they different? Well, this one always halts and this one may not halt. Right? So, right? And the problem, if m doesn't halt on m, then this one runs forever. Right? So let's talk about a third problem. Here are three problems. Right? This third problem is the halting problem. Given an m, all it needs to know, on any input, it needs to stop and give the right answer. All it needs to know is, does m halt on m or not? That's all it needs to know. Yes, no. Does it halt on m? Right? And we want to prove that this is undecidable. All right? And how do we do it? We do it by contradiction. We're going to be proving lots of things are undecidable. And the way we prove they're undecidable is by pretending we have an algorithm for them. Right? Right? We want to prove this doesn't have an algorithm. How do we do it? By way of contradiction, let's assume it does have an algorithm. Right? And if we have an algorithm for this, we're going to write a program to solve this problem up there. Right? Does that make sense? If we have an algorithm for this, it'll give us an algorithm for this. But there's not an algorithm for this, so there's not an algorithm for this. Right? Does that make sense? Everybody follow that? Right? If you could solve this, you could solve this. Right? Here's the algorithm. Right? Now what we're doing is we're describing an algorithm for solving the not diagonal problem. All right? What does it do? What does my algorithm do? It takes this input in m, right? And I want to know what m does on m, right? But the scary thing is, I always need to halt. I'm happy to simulate m on m as long as I know it halts. So what I first do is that I don't first start running m on m. I first ask, right? I first call the halting problem, right? Because we assume that we have an algorithm for the halting problem. And what does the halting problem do? It tells me whether or not m halts on m. Right? It tells me, yes, it halts. No, it doesn't halt. Right? So if the halting problem tells me that it does halt, then it's okay. I need to know, what does it do? Right? But now it's safe for me to run it. I can run m on m. And I know it'll halt, and I'll know what it does. Right? Right? But if the halting problem tells me that m doesn't halt on m, then I already know what m does on m. And I don't have to run anything. Right? Does that make sense? Am I completely killing you? I know I'm completely killing you guys. Right? But hopefully you'll get some of the flavor of this. Right? If I could solve this problem, I could solve this problem. Right? Either way, I know what m does on m. Right? So, but I can't solve the not diagonal problem, so I can't solve halting problem. So the halting problem is undecidable. Everybody dying? How are we doing for time? We go to 4. So we have 7 minutes left. Right? Is that right? 7 minutes left? Hey, this is pretty good timing. All right? Do we have any other? Here's poetry that some students sent me. This poetry proves that the halting problem is undecidable. Right? All right, so what am I going to ask you? I would like you to have some basic understanding of what these objects are. All right? So, for example, I could ask you on a test, describe to me what is the halting problem, right? Here's the halting problem. The halting problem, it takes as input a Turing machine and an input, and it tells me whether that Turing machine halts on that input, right? You should know that, right? If you're in computer science, you should know what the halting problem is. Everybody good? What's the not diagonal problem? Now we're getting a little bit more esoteric. What's the not? Well, what it does is it takes as input the description of a Turing machine, and it does anything different than n does on m. Right? Everybody got that? It's the not diagonal problem. In fact, I've had on questions, on tests. I know I've had a question. Tell me what the not diagonal problem is. And as you do it, well, it's the diagonal of what matrix? Right? So you'll have to know these are the Turing machines, and this is the input, and the diagonal is what M does on itself, and it's the not diagonal problem. Right? Bang, bang, bang. You should know that. You should know that. Right? All right, so here, could I ask this on a test? Prove to me that the not diagonal problem is undecidable. Right? What would you do? You'll say, I have to prove that every Turing machine M fails to solve this problem. Why? Because on why does M fail to solve the problem? M fails to solve the problem because on input M it gives the wrong answer. Right? That's the entire proof. Right? Really, if you wanted a quick, I give you this much space. Describe P diagonal for me. On input M, it does anything different than M does on M. Okay, prove to me that's undecidable. You give me a Turing machine, I know it doesn't solve the problem because M on M does what M on M does. It doesn't do something different. Right? Right? That's the entire proof. Right? Argue that P halting is undecidable. Well, if P halting was undecidable, then P not diagonal would be, if halting was decidable, then P not diagonal would be decidable. But it's undecidable, so the halting problem is undecidable. Right? And here at some point I wrote up the proof in case you wanted to sort of go into detail. And I've had questions where, well, I make you give the whole proof, but I think that's, right? Probably won't do that. Just give you a little testing about it. Right? And then in the past I've made people give little nuanced changes to it, but that's not going to happen. All right? How many minutes do we have now? We have 4 minutes. Excellent. All right? So, remember, I don't know, were you guys here then? We had a strike. Were you guys around for the strike? Right? Well, I was teaching this course during the strike. And so I wasn't supposed to lecture, but I kept lecturing for anybody who would want to show up. And then I gave people tests, but I didn't have TAs to mark them. And I was lazy. So I had a multiple choice test. Right? And right? So here's the multiple choice test that I gave them. All right? So here's the statement. There exists a Turing machine that solves P, right? P is computable. Here's P is uncomputable, right? Oh, that's supposed to be a not there. Sorry. All right, so here let's ask. I always, in true-false questions, when you're supposed to choose one of 5, usually say which of these 5 is true, but I have a hard time coming up with 4 things that are false. So my multiple choice questions are always, which of these is false, right? So which is false? Is Turing machine, right? M is a Turing machine which is computationally the same as a Java program, right? That's true. P is a Java program. P is a computational problem like sorting. Yes, right? I could be the description, the input could be the description of the Turing machine, right? That's true. So which one's wrong? B, right? Multiple choice question. B. Here's another one. These 2 lines, assuming there's a not there, these 2 lines say the same thing, right? Oh, no, this is, sorry, that isn't uncomputable. This is one, it's just bad, right? It says for every input there's a Turing machine that solves the problem, right? It's not uncomputable. It's the bad sentence, right? So I didn't spend so much time on first-order logic. One of the reasons I spend a lot of time on first-order logic is I asked these students after taking a course from me the difference between these two lines, and nobody knew. All right? So now you should know, right? Do these two lines say the same thing? Absolutely not, right? So that's the false one. Right, exactly. You would have a different machine for every input, right? So here, actually 50 isn't a problem. You could have an infinite number of machines, right? Well, each input has a different machine. Anyway, here, the first line requires one Turing machine that must correct on every input. The second one allows a separate machine on every input, right? That's right. Those are right. All right, so the halting problem tells me whether M halts on I. That's right. The task of halting problem is to ensure that it halts, right? That's wrong. Halting problem is a classic undecidable problem, right? Everybody good with these? It's not a hard test, right? Given enough time and resources, any computational problem can be solved on any given input. Is that true? No. Some problems are undecidable. There are computational problems that each algorithm fails to give the right answer for on some input. Yes. Right? So it's this one. I think we're running out of time. How many have we got left? That's it. Right? You can do this last one on your own. Have a good 2 days.